Hey, what's up, AP Calculus students? This video is just going to talk about limits at infinity. And limits at infinity are when x approaches positive infinity or x approaches negative infinity. So given a function f, it is the limit of f of x as x grows without bound. These limits at infinity also tell us about the end behavior of the graph. So, to let us know if our function has a horizontal asymptote. Okay, so what we're going to look at first is just some polynomials here. So if you have the function f of x equals 3x to the fifth, that's what its graph would look like. If I wanted to say the limit of that function as x goes to infinity, well, you have to imagine that x to the fifth is going to get infinitely large as x goes to infinity. If you multiply that by 3, it's still going to get infinitely large in the positive direction. So without doubt, this would be positive infinity. And we can see the right end of the graph approaches positive infinity. So we do not have a horizontal asymptote since it grows without bound. So if we come over to this function, g of x equals 3x to the fifth minus 4x cubed plus x squared minus 1. The graph looks like this. And if we didn't have the graph there, but just wanted to say what the limit of that function was as x goes to infinity, well, the term with the highest power is actually the one that controls the end behavior of the graph. So you can kind of just ignore all those other terms except 3x to the fifth. We know from before the value of this limit is infinity. So that means the value as x goes to infinity of this function would be infinity as well. Okay, so the term with the highest power controls the ends of the graph. All right, so keeping that in mind, we should be able to figure out these limits pretty easily. So here's a polynomial. The terms aren't in the correct order, so I'm just going to focus on the term with the highest power. It should be negative 4x cubed. So I could use that term to get the value of the limit for the entire function. So as x goes to negative infinity, x cubed is also going to approach negative infinity because cubing a negative is still negative. But when multiplying by negative 4, that's going to switch the value of our outputs. So in reality, we're going to be approaching positive infinity for this one. So if you remember what the shapes of these polynomial functions look like when the leading coefficient's negative and the highest exponent's odd. So I'm just going to make a note that's negative for the coefficient, odd for the highest exponent. The graph looks something like this. So our left end would be approaching positive infinity in this case, and we'd have no horizontal asymptote. So why don't you pause the video so you can just do this next three, and you can write your work the same way. We'll check it out in a second. Okay, welcome back. So feel free to pause the video just to check how I wrote my work. But I'll just discuss number 3 very quickly here. So we're just going to take that term with the highest power. X is approaching negative infinity, so to the fourth power is going to take us to a positive, multiplied by a negative takes us back to a negative again, so that's going to be negative infinity. I just sketched what these graphs would look like and circled the end that we were talking about. Alrighty, if you guys flip the page, next up we have a little limit theorem here that we're going to discuss. So if you are doing limits as x goes to infinity or negative infinity of a function written this way, where the numerator is a constant and the denominator is x to some positive value of n, in both cases the value of those limits would be 0. So here's just a quick little example to wrap your minds around. So if we're doing limit as x goes to infinity of 3 over x to the fifth, the denominator is going to become significantly large as that x goes to infinity, but the numerator is going to remain 3. So when you take a constant and divide it by something that's significantly large, your answer is going to be close to 0. And the larger that denominator is, the closer the answer is going to get to 0 over time. So we're going to use that concept to just answer this next batch. So looking at this first one, I'm just going to rewrite my problem using an exponent. So the constant in the function isn't going to be affected by x approaching infinity, but if we come over here, as x goes to infinity, square root of x is going to get significantly large. We have a constant at the top. So when we evaluate this limit, our constant's just going to stay 2. This fraction is going to approach 0 in value. So we could say that the limit is heading towards 2. Okay, moving on to the next one. This is one where if we have a polynomial or a monomial, we could rewrite the problem first by dividing everybody by x cubed. So it would give me -6 plus 3 over x plus 10 over x cubed. And as x tends towards infinity, the values of these fractions are going to head towards 0. And then we'd just be left with this constant of -6, which is our final answer. Okay, now here, because there's 2 terms in the denominator, if I wanted to divide it, I'd have to do a long division. But if you think about our limit laws, we have the limit of a quotient here, and that's equal to the quotient of the limits. So we could think of the limit of the numerator over the limit of the denominator. And since the numerator and denominator are each polynomials, we could actually just focus on the leading terms in both the numerator and the denominator, kind of like we were doing on the front. Now we could simplify that ratio by just calling that 3. And now we're just left with a constant. As x goes to infinity, this is just going to stay at 3. So that would be the value of our limit. Okay, so why don't you pause the video, see if you could do number 9 and 10. You could do it just like number 8 and set up the ratio of the terms with the highest powers and just see what you get. Okay, welcome back, guys. So for this one, I just did the ratio of 3x cubed and x to the 5th, since those are the highest powers in the numerator and denominator. That simplifies to 3 over x squared. And as x goes to -infinity, that denominator is going to get infinitely large. So the value of that function is just going to approach 0 as x goes to -infinity. All right, for this one, I have x cubed over x. That simplifies to just x squared. And as x goes to -infinity, because we're squaring it, the value of the limit is going to be positive infinity and not negative infinity. Okay, so that takes us to our definition of a horizontal asymptote. So how does this go? Well, the line y equals L is a horizontal asymptote of the graph of f if one or both of these are true. So one is enough to have a horizontal asymptote, meaning the limit as x goes to -infinity of f of x is L, or the limit as x goes to positive infinity of f of x is L, and L is some constant. All right, so it can't approach infinity or negative infinity. It has to approach a constant to have a horizontal asymptote. All right, so if the left end is approaching, let's say, 5, and the right end is approaching 3, well, your graph would just have 2 different horizontal asymptotes, one at 5 on the left side, one at 3 on the right side, and that's okay. All right, so which functions from above have horizontal asymptotes? So if we just go back to those 5 example problems there, for any of these limits where x goes to infinity or negative infinity, if the value of the limit's a constant, that means that function is going to have a horizontal asymptote. So it looks like all of them except number 10 are going to have a horizontal asymptote. So I'm just going to write that down here. So for number 6, my horizontal asymptote would be written as y equals 2. Number 7, we could write it as, we'll say HA, be y equals -6. For number 8, we're going to say y equals 3. And for number 9, we'll just say y equals 0, which is just the x-axis. All right, guys, that's where I'm going to stop this video. So if you have any questions, just let me know next time I see you in class. Toodles.